Okay, so we will talk about shortest path problem. In a graph, in a directed graph, suppose we have a directed graph G, V comma E, where E is the set of V is the set of vertices, E is the set of edges, and we have a edge function, we have a edge weight. So, this is basically a function from h to the real number. So, this is the weight function. Okay. Now, what do you mean by path of a graph? Suppose we have, how to define path? Suppose we have two nodes u and v. Now, suppose we have some intermediate nodes, say v1, this is the directed graph, v2, v3 dot dot dot, vk, and then this is. So, path means a physical path. We should able to go from, by follow the direction, we should able to go from u to v. This is a path. Now, what is this weight of this path? Weight of this is a path p. Now, weight of this path is basically, this is the sum of the weight u v such that this u v is belongs to this path. So, we just count, if suppose if this is a example, suppose v1 and we have a v4 and we have some intermediate vertex v3. So, this is a v3, v4, v5, and say this is v6. This is a v6 and weight at say 2, -1, 3, -6. Suppose these are the weight. Now, this is a path. This is a path from v1 to v6. This is v6. Now, what is the weight of this path? Weight of this path is basically sum of the edge weight. So, this is 2 -1, 3. So, this is basically 5 minus, so -1 and -1, this is -2, basically sum of the weights of this path. Okay. So, now we want to find out the shortest path between two nodes u and v. So, if you denote that weight of the shortest path by delta u v, this is basically minimum among all the path weight, where p is the minimum among all the path weight, where p is the path from u to v. So, we consider all the path from u to v. Now, whichever is the minimum, so that path we take, and the weight of that path is denoted by this delta of u v. Now, when, so if there is no physical path exist from u to v, or then we say u v is infinity. If there is no path from u to v, then we say no shortest path exists. So, we want to see whether optimal substructure exists in this case or not, so that we can think for dynamic programming approach to solve this problem, finding the shortest path. So, optimal substructure means, suppose we have a shortest path from u to v, and in the middle we have some nodes x, y. Suppose this is the shortest path from u to v. Now, if you take this path from x to y, so then this will give us, this path will give us the shortest path between x to y. If this is true for all nodes, then this is called optimal. So, if not, so we can prove this. If suppose there is a path from x to y which is shorter than this path, then what we do, this is called cut and paste technique. So, what we do, we take this path, a new path from u to v like this, we go from u to x, then we take this path, then from x to this. So, this is a new path from u to v, and this is lesser than the path which we have. So, it contradicts that our original path was the shortest path, because if this is a shorter path from x to y. So, this is the optimal substructure property is happening here. So, we could think for a finding the applying the dynamic programming approach, but we want to look at whether we can apply greedy approach or not. So, yes, we can apply the greedy one. So, that is the Dijkstra's algorithm we will talk about. Now, that is based on a inequality which is called triangular inequality, triangle inequality. So, what is a triangle inequality? Suppose we take 3 vertices u x v belongs to capital V. Now, it is telling delta of u comma v is less than equal to delta of u comma x plus delta of x comma v. So, how to prove this? This is for any 3 vertex x, u, v and x. So, how to prove this? We can prove it graphically. So, suppose we have this vertex u, v and x. Okay. So, this is the shortest path from u to v, delta of u comma v, and this is the shortest path from u to x, and this is the shortest path from x to v. Okay. Now, why this is true? Because see, if we take this path u to x, then x to v, what is the weight of this path? This plus this. So, this is a path. So, this path must be, weight of this path must be lesser than the weight of the shortest path. This is the weight of the shortest path. So, hence this is less than the another path. We got a path, and weight of that path is delta of u x plus delta of x b. So, this is the proof. Proof is straightforward from this picture. Okay. So, this is called triangular inequality. Now, we talk about when the shortest path may not exist even though there is a physical path from u to v. Suppose we have a node u and we have a node v. Suppose there is a physical path from u to v. Okay. Even though there may not exist the shortest path, when if suppose there in this path, suppose there is there is a negative cycle. Suppose this is a x intermediate node, and we have a negative cycle. So, we have a cycle whose weight is negative cycle in the path, then the shortest path will not exist, because why? Now, if you give me this is the shortest path, I will make another loop to reduce that. So, we cannot find out a shortest path if there is a negative cycle. So, negative cycle in a path means no shortest path exists from u to v, no shortest path. Okay. So, negative cycle will not give us the shortest path. Now, we will talk about a algorithm which is Dijkstra's algorithm, where we assume there is no negative cycle. So, that means to guarantee that we assume all the edge weight are positive. So, no edge weight are negative. So, that if all the edge weight are positive, there is no question of negative cycle. So, this is the problem of single source shortest path problem. And here, so here we have given a graph g comma e, and we have this is Dijkstra's algorithm KSTRA. We will talk about Dijkstra's algorithm. So, for Dijkstra's algorithm, we have assumption on this weight function W, which is basically R plus. So, we are not allowing any negative weight h to avoid the negative cycle. Dijkstra's cannot handle the negative cycle. And we have a source node, this is called source vertex, from which, so this single source from which we should be able to find the shortest path from any other vertices. So, basically you are trying to find u comma v, where v is any other vertex. So, this is the, so this approach is a greedy approach. So, the idea is we maintain a set S, capital S, of vertices whose shortest path from S, shortest path distance delta basically from small s are known. Okay. So, that means this is our set S and this is the vertices v minus s basically. So, now if we are not allowing any negative h, then the smallest must be in S, because if we are in small s, so best way to go to the smallest is we remain in small s, because we are not having any negative cycle or any negative s. So, that is the best way. So, we start S with the smallest and then slowly we capture the nodes with this. So, that we will write. So, at each step we add a node, add to S the vertex from v minus x whose distance estimate is minimum, whose distance estimate from S is minimal. So, that means, so we have some vertices over here. Okay. Now, this is having some distance estimate, that means the path from S to that node, what is the cost. Now, we choose the vertex v which is having distance estimate minimum among this. So, we capture that S v into S and then we, so v is having some adjacency vertex. So, now v is in S, now we will change the distance estimate of this adjacency list of v. So, that is the idea. So, then in the third step we update the distance estimates of vertices in adjacency list of v. We continue this until this became empty, I mean everything will be in S. So, that is the idea. So, let us write the code. So, this is a greedy choice, which is the minimum, we are taking that. So, that is the greedy approach. So, let us write the pseudocode for this, then we will take an example to execute that code on that. So, this is the pseudocode for Dijkstra's algorithm. So, input is a graph and a source vertex and a edge vector, which is okay. So, what we do? We just put the degree of the source vertex as 0 and the remaining degree is infinity. So, that means the distance estimate is that those vertex are not yet explored. So, for all V belongs to V minus S, we put the distance estimate of that vertex as infinity. Okay. Now, we initialize this by empty, and now we take a priority queue. Q is V, which is a priority queue, which contain all the elements of V minus S, and then slowly we will extract the this minimum distance estimate. So, we will extract the node which is having the minimum degree. So, and this will continue until while Q is not empty. So, this Q is a priority queue. Okay. So, while Q is not empty, what we do? We extract the minimum element from this queue. This we can implement either in array or by heap. We know the heap priority queue implementation. So, now this we will going to add in S. Okay. So, now we will check all the adjacency vertex of S for each all the adjacency vertex of U. So, this U is now added in. Now, we check all the adjacency vertex of U. Suppose V is the adjacency vertex of U. Now, it was having a distance estimate. Now, if we check that dV for each adjacency vertex of U, you check the dV, the distance estimate which it was having. So, that means there is a path from S to this node. Now, we got a new path. We can come from S to this node by du, then we can take the direct path. If that is better, then we replace that by this. So, if dV is greater than du plus wuv, this is the new path. So, that means we can come from S to this is S source node, S to U, then we can take this direct path. If that gives us better distance estimate than the earlier, then we should replace that. Then dV will be replaced by du plus wuv. So, this is what is called this step. This is called the relaxation step. We are relaxing the relaxation step. Okay. And this is also called the decrease key. This we need when we talk about the time complexity, how we can go there and change it. So, this is the code. This is the pseudocode for Dijkstra's algorithm, and this step is the relaxation step. We will try to relax each of the vertices which is adjacent to it. Okay. So, let us take an example. Let us take a graph. So, suppose A, B, C, D, E. So, this is the connection. So, this is a directed graph. Okay. So, this is a diagram, and we have to give the weight, and we are not allowing any negative weight to avoid the negative cycle. 2, 8, 7, 9, 2. Suppose this is the graph, and we have to execute this Dijkstra's algorithm on this. Okay. Now, suppose we choose this as a source vertex. So, this is the priority queue. So, A, B, C, D, E. So, we are keeping the distance degree. This is the source vertex 0, others are infinity. That is what we are doing in the initialization step. This is the initialization step. We are keeping the degree of this source vertex is 0 and remaining are infinity. Okay. So, now S is initialized by empty, and this everything we put into the priority queue. Now, we extract the minimum. So, minimum is basically this one A. So, we put A in S. So, this is our U. So, this is our U now. Now, we execute this. So, we check all the adjacency list of u. So, this is in adjacency list of this is V adjacency list of u. So, this was having the degree, this was having the degree infinity. So, now this will be replaced by, so this 10 and this will be replaced by 3. Okay. So, this B is now 10 and E is now 3 and this will be remain unchanged. Okay. So, now this will be remain unchanged means these are infinity. Now, we take the extract the next minimum. So, that is 3. So, that is basically C, okay, C node. Now, this is our U now. Now, this is our U. Now, who are the V? V is the adjacency list. So, this is V. Now, we check the degree of this. It is infinite. It was infinity. Now, we have a path from S to this node by S to this node by 3 and then we have this 2. So, this will be now 5. Okay. So, that means this will be E is now 5 and this is also now this will be 11, this is D, D is now 11 and now we have this path. So, it was having a distance estimate 10, that means there was a path from S to this node with a cost 10. Now, we have a new path. What is that? We can go from S to this node by cost 3 and then we can take this direct path 4. So, with a cost 7. So, 7 is better than 10. So, we can replace that 7. Okay. So, now this B is now 7 and these two are already in S. So, this is C. Now, we take the next minimum. So, this is the 5, that is basically E. So, now we check the adjacency list of this. So, this is now V is this. So, now this was having a distance estimate 11. So, that means there was a path from S to this node with a cost 11. Now, we have another path, we can go to S to this node with a cost 5 and then we can take the direct path 9. So, 5 plus 9 14, which is not good as 11. So, we keep the earlier path which is better. So, we are not relaxing this edge, we are not relaxing this node. Okay. So, now which is the minimum? So, this will be remain unchanged. So, 7 and 11 will be remain unchanged. So, now 7 is the minimum. So, 7 is the minimum. Now, we take this is now U. Now, we take all the adjacency list of this. So, this is one adjacency vertex V. So, now it was having distance estimate 11. Now, we have a new path. So, we can go from S to this node with a cost 7 and then from here we can take this direct path 2. So, 9. So, 9 is better. So, this will be replaced by 9. So, D is now 9. Okay. And the remaining one, so we have this one. So, we can just have a cross verify. So, this is having distance estimate 3, which is already in S. So, we may not need to check that, but to be a cross verify. So, now we have a new path. We can go from S to this node with a cost 7, then we can take the direct path 1. So, 7 plus 1 8, which is not good at 3. So, whoever is the node in S, then their distance estimate is done. So, if a node V is in S, that means their degree is basically delta of S comma V. This is the correctness. So, once we capture a node in S, then the degree is becoming the minimum distance estimate from S comma S to that node. So, then we take 9. So, 9 we can just have a verify whether this is better because yeah. So, then all done and these are basically deltas. These boxes are basically deltas of S comma that node. So, here we are not allowing any negative cycle to avoid the negative cycle, we are not allowing any negative weight H. So, now what is the time complexity for this? What is the run time for this? So, to calculate the run time, we have to check to calculate the runtime, okay. So, how to calculate the runtime for this? So, time complexity for this. So, time will depend how we are implementing this priority queue, whether in array or the heap. So, basically this is of order of v times this loop, because this is of order v and then this is also of order v, and the inner loop. So, this loop, for each of these adjacency lists, this loop is basically, this is the degree of u basically. So, if we take the sum of this degree of u, this is basically give us order of E by handshaking lemma. This can be proved. So, sum of the degree is order of E. So, basically what we are doing here, we are extracting the minimum, that cost we do not know, it depends on which data structure we are using. We are using a array or heap, and then we are decreasing the key. So, if the relaxation is done, then we are going to that particular node and we are changing the degree. So, that is sort of decreasing the key. So, the time is basically same as time for Prim's algorithm. So, time is basically order of v, I mean size of v into the time required for extract the minimum plus order of E and the time required for decrease the key. Okay. So, now if we, depending on which data structure we will use for our priority queue, the time will be depends on that. So, let us just write that. So, this is the runtime. So, now if we implement the priority queue using say array. So, this is the time for extract the main, and this is the time for decrease the key, and this is the total time for this time, total time for Dijkstra's algorithm. So, if we just use the array for array to have this priority queue, we are putting everything into the array, then how much time will take for extract the mean? So, minimum will take, we need to read all the elements. So, this is basically order of v, and decrease the key is just we go to that particular position and we change the value. This is basically constant time, and then this will be v square basically. Okay. Now, if we use the binary heap, mean heap, then the decrease the key will take extract the mean will take, because minimum is in the root. So, if we are using mean heap, so we will just take it that, and the heap property is violating mean heap property. So, we need to have the mean heapify. So, that will take basically order of log v, and this is also order of log v. So, this is basically order of E log v. Okay. So, this is the time complexity for Dijkstra's algorithm. Thank you.